Hello everyone, yes, and I'm still building my own CPU, and that's the really simple CPU built from a standard Gates. That's 8-bit CPU, stack machine, so I don't have classical register file, instead I have a stack that can be connected to my ALU. I already worked on my instruction set architecture, I already have my tool chain. On the last video I've been working on the ALU and I have a couple of changes in the ALU. So first of all, I decided that my ALU inputs and output will be stack centric, so I swapped X in and X out. So now X out is coming from the X register to the ALU and the output of the ALU comes to the X in, like it comes to the X register. The second thing that I did is I made a test vector. In the Logisim, you can create a text file describing all your inputs and outputs, and Logisim will automatically apply those inputs and outputs to your circuit and check if the actual output is the same as expected output. So that's some kind of a unit test in the Logisim. As I have just 8-bit ALU, I actually generated those files for all possible combinations of all the operations, all inputs, all outputs, and this gave me like more than 300,000 ops, so it takes like 15 minutes. Everything is in GitHub. And speaking of ALU, the next logical step after ALU is to build my stack, and I will remind you that I have a stack machines, and it means that I have a stack consisting of 4 registers, and values can move inside of the stack like up and down, they can be pushed and popped. And my X and Y registers are always connected to the ALU, which means I don't need to specify the operand of my operations, because that's always X and Y. This makes some things simpler, this makes some wiring simple. This probably makes programming this machine a little bit more complicated, but still it works. And I also have X0 register that stores the previous value of the ALU operation. The values can be loaded into stack from several sources. Well, of course it goes from ALU, but I also have commands like load immediate, so you can load a value directly from your opcode, and if it's between 1 and 63 it can be set directly. For the other values you have 2 operations like loop and poop, and those operations load the upper nibble and lower nibble of the value, like not touching the other one. My values can also come from the memory, register file, and so on and so forth. I also have a lot of stack special operations which are specific for stack machines, and they operate just in a stack. First of all, I have push the stack, which like moves all the values up, dropping the value of the T register. I have exchange that swaps values between X and Y registers. I have rotate the stack, it's like more popping the stack down, so everything moves down, but the value of X is not dropped, instead it's copied to T, so it's like going in a ring, that's why it rotates the stack. I have a return previous value that copies value from X0 to X, and X0 goes to X, X goes to Y, and so on and so forth, so it's like push but from X0. I have pop, which is more like RTS without actually making a ring, so value of X disappears, and that's all the operations. So knowing the operations, knowing the number of registers that I need, I will create a new circuit. So I will call the stack, because I will have 2 stacks, I will also have a call stack, but this will be the stack. It has 1 input, X in, it has 2 outputs, Y out and X out. Inputs and outputs, they are 8 bits wide. And then I need to put the registers. I actually have 2 versions of registers here in Logisim. I have a flip-flop, and the flip-flop is a register that constantly updates its value. So on every cycle it reads a new value from the input and stores it, and on the next cycle it sends it out. Instead, I'm going to use another one register, which is more like a storage register. And the difference is that it has a write enable pin, so it only updates its value when write is enabled. And if you don't need to update the value, you don't set this pin. I need those for X, Y, Z, and T, and I'm going to use in my hardware, I'm going to use the register that have output enable pin. So when output is not enabled, the register output goes to high impedance state, but here I don't have that ability, So instead, I'm going to imitate it with a buffer. Well, having all the 5 registers, I can connect them. Output is pretty simple. X goes to X out, Y goes to Y out. The rest of it, well, obviously X0 is only fed from X. And for the other registers, they are usually fed in pairs. Like T can get value from X or Z. Z can get value from T or Y. And Y can get value from X or Z. So I'm going to draw all of those pair connections. And for the register themselves, I will use multiplexers because that's a perfect use case for a multiplexer. I have 2 inputs, I have 1 output. I need to choose which output goes to which input. This will be part of my control logic. For the X, it will be a little bit more complicated because I have several sources. X can be fed from Y, X0 or T, or external sources. I would like it to work like a bus. So it will be pulled up and all the devices on this bus will have open drain connector. And there will be several devices like ALU, like fetch model, fetch and decode, RAM module, register files, and so forth. So I will use the exactly same approach to connect my other registers like T or Y or X0 to the same bus. With one small exception, as Y is always connected to the Y out, I cannot use the output enable pin of the Y register. Y should be connected all the time, and because of that I will have a multiplexer that will choose the input for X between Y register and the X in bus. Another one option would be to put a tree of multiplexers, but I don't want to go that way because propagation delay. We'll discuss propagation delay today one time. Having all of this connected, I have several control pins, control inputs. I have multiplexer inputs, like I have multiplexer select pins, I have write enable pins, plus I have my output enable, which is not a real output enable but a buffer here, but in the hardware it will be output enable. In total I have 12 pins. How do I control them? Let's think on how many operations do I have and how many pins do I have. For example, I have X write enable and X multiplexer. It's just 2 pins for the X register. First of all, I have like 4 operations of loading data. That's immediate, loop, whoop, and clear. Obviously, for this, it should be both true. Like I would like to write to the X register and I would like to choose the input from the bus. Second one, exchange. I'm getting value from Y, so I'm still writing the X register, but the multiplexer goes to false. I'm choosing the other one. I'm going to write the whole truth table for all the operations and all 12 control pins. And actually, I don't have a real operations here, not just the real operations, because I will have things like unary ALU operation and binary ALU operation. This is not an opcode. That's not an opcode, but that's just a mapping for some opcodes. And I need to distinguish unary and binary, because for both ALU operations, X0 is set from X, but for binary operations, a pop operation should also be done. Having this table, what should I do next? The first option, I can probably go to some, I don't know, optimization software, put this table into that software. I have 8 inputs, I have 12 outputs. Like those 8 inputs, they are one hot coded. Well, actually, I have no idea where to find the open source software that can operate with such a big table. I can do it manually. But I don't want to do it manually. I mean, I don't want to make the optimization manually. I don't want to infer the proper logical function. Instead, what I can do, I can start picking one pin by pin. For example, X0 write enable, it's only true for the operations. So, okay, I know now that I need to check if I have either ALU unary or binary operation, that's OR gate, and connected to write enable. Same goes for, say, X write enable. It's only false for push the stack, because I don't update X on push the stack. So I need to check if I'm in the middle of the push the stack operation and put a NOT gate, and so on and so forth. So I do this for every control pin, and I build a small control circuit like on a pin basis. And as most of the control pins are pretty simple, for example like T write enable and T multiplexer, they are only true for say PTS and RPV, but T output enable, T write enable is also true for RTS. I can do those just in 2 OR gates and connect all the T. So this is really simple if you think about it in a per pin approach. Some of them like XMUX, they are more complicated, but most of those gates are pretty small. And this is it. But I need 3 more things. I have 8 input pins, so you already know I don't want to transfer 8 signals. I would like to use a decoder, so that will be 3 to 8 decoder. Plus I need to connect clock and reset signals. I need a reset signal because my registers will be in undefined states after powering up. Like you turn them on and they have some random content. I don't want my CPU to start from a random content because there's no way to get rid of that content. Instead, I would like it to start in some predefined state. In case I would have an FPGA or even in Logisim, you can set a reset value for each register, but in the physical hardware that I'm going to use, it always resets to a 0. Well, there are some versions that resets to a 1, but I'm going to use the one that resets to a 0. You cannot set a value, because otherwise you will need 8 more pins for the reset value input. And I will have another one circuit that will generate a reset signal in the beginning of, like after the power up, it will generate a reset and reset all the registers to 0. And this is why I would like to have my knob operations to be all zeros, because that's the default state of the registers. Plus, I need a clocking input. And the clocking input, that's a really interesting thing. Like, why do we need a clocking at all? Like, what's the physical reason for this? And the reason that we have a propagation delay. Last time we discussed the propagation delay in the ALU video, but I will go through it one more time. Usually, people think of electronical circuits as a super fast circuit. So you change the input and the output changes immediately. In fact, you change the input and the output of a gate changes with some delay. We call it propagation delay. And what's even worse, those delays are combined. So in my case, I have 3 gates between input A and output Cout. That's XOR and OR gates, like 3 gates, and all of them, like you first change the input of XOR, so the input of AND is up with a delay of 20 seconds, so the output of AND changes with a delay of 20 more seconds, input of the output of the OR changes with a delay of 20 seconds, and this is the critical path type, that the longest path that signal needs to travel, that's the critical path, and this is the delay for your whole circuit, maximum delay. So in my case it will be about 60 seconds, but that's not all. I'm combining my single bit adder to 8-bit adder. The ripple carry adder, chain of 8 1-bit adders, which gives me the total path of about 500 nanoseconds. Like my critical path, my total delay of adder is 500 nanoseconds, plus I have that control add sub model, so it's maybe 150 now, plus I have some control logic in the ALU and so on and so forth. So maybe it's like closer to 600 nanoseconds. And then in my CPU I connect my stack to the ALU. So Xout is sent to Xout, Xin is sent to Xin. But you remember that in the stack the X is the same register. So when you make say a negation or addition, when do you write the X in? When do you store it? You need to wait for this 600 nanoseconds before you store it. And that's why CPUs are limited in clocking. Well, that's not only the reason, but one of the reasons why we are limited in our clocking. The clocking speed needs to be at least slower than the longest critical path. And this way, with the clock, we say like, hey, on the falling edge, the value is presented on the output of the register, and all the sequential circuits are going to update the signals. On the rising edge, we expect our signals to stabilize, and we sample those signals and store them in the register. And I also been asked, like, why the signal, like why the clock signal is squared. And the reason for that, I almost explained you, that we need to wait for the sequential signals to stabilize. And for this, we need to have some pretty strong and easy detectable long period. Like we have a long period of low voltage, or long period of high voltage, doesn't matter. And we would like to minimize the change time, like rise time or fall time between those levels. We would like to minimize them because, for example, let's say we have a source signal. It hits the zero and immediately starts to grow. Of course, the low level signal is not just zero, it's like 0.8 volts, so you can make your source signal pretty wide and it will just limit your clock speed. It's more convenient to use that kind of signal. And as we are using the CMOS logic, the logic that operates in just the positive side of the voltage, so it requires voltage between 0 and some positive value, like plus 5 volts, plus 3.3 volts. We cannot use, say, for example, sine wave, because we can make a sine wave with a really great rise and fall times, but it's negative, so we have to stay on the positive side. And this is why this signal is square, and this is why the signal is just positive, because it's limited by our hardware and it's limited by its purpose. We would like our fronts to be as vertical as we can. Well, there are some issues with the ringing and like reflections, but in general they need to be perfect. And this is it. Well, actually it's not, because after the stream I realized that I forgot one important thing. I forgot my knob command. I discussed my knob several times. I told you that I need a knob, and I forgot to add a knob operation to the stack. I forgot to add knob operation to the stack. And why do I need it? Because the knob operation means nothing changes. And for the ALU it's been not important, because for the ALU you don't store any data. You update signals on the input, you get the update on the output. For the stack you actually sample the values and store them, which means you need a special command like don't update the value. Instead of sending 3 bits into my decoder, I will send 4 bits, but the 4 will be used to control a set of gates, of AND gates, that will either enable or disable the right enable pins. In this way, whatever is on the op side, whatever the command is, whatever the other 3 bits is, and whatever the decoder selects, if I don't have 4th bit enabled, all the right enables are gated and no update happens. And that's it. I already did manual checking, it works, but I probably need a proper test bench. And for the next video, I think I should work on the register file, which will be simpler, but a little bit more complicated. We have to handle increasing and decreasing of values. So, thanks for watching, and see you on the next video.